So my name's David Hughes. I'm from the University of Leeds, and our program is on anti-diffusive dynamics in turbulent systems. Typically, in a turbulent system, one might have diffusion. So one could think, for example, of putting a blob of ink in a turbulent flow and it would spread. But there are remarkable processes where the transport is up gradient rather than down gradient, as in a spreading ink blob. And they're what we would call anti-diffusive or negative viscosity phenomena. And rather than leading to spreading, they lead to sharpening. And one particular feature which comes up a lot in anti-diffusive systems is layers or staircases. So these would be regions of strong gradients separated by wider regions of mixed flow and things. And so, as I've described it so far, that's sort of talking about fluid dynamics, but anti-diffusive dynamics occurs in a whole range of physical and biological systems, and they're represented in our program. So, for example, you might have the flows on Jupiter, the banded flows on Jupiter, which are a staircase in potential vorticity. In the oceans, we have what are called double diffusive staircases, driven by the disparity between the diffusion of heat and salt. Very different area, we have turbulent states, self-organized turbulent states in fusion tokamaks, so-called E cross B staircases. And in yet another very different area, in active matter or biological matter, we can have structure formation, and it might be on a small cellular or even sub-cellular scale, or on a much larger scale, such as flocking of birds and animals. So anti-diffusive phenomena are widely observed in nature, in experiments, in computations, but they're not really understood, which is why we're all here. And one of the beauties of this program is that it brings together people from all these different areas of physics and biology that normally wouldn't meet. Normally conferences are subject specific and you wouldn't necessarily meet people from all these different areas. And we sort of have two goals. So one is to understand what we're all doing in all of these different areas. And the other is to then see what phenomena are in common. What is the common features, if indeed there are common features, of all these very different anti-diffusive systems, because through understanding that, then we'll be in a much better position to understand theoretically and mathematically these interesting phenomena.
So my name is Guilhem Dif-Pradalier. I'm from CA, France. So I mostly work on fusion and plasma research. I think this is a very interesting program because, well, we come from our day-to-day, on a day-to-day basis, we have different problems that we each of us want to solve, but we all share in common the fact that we are dealing with nonlinear self-organizing systems. And those systems, they seem to display they have quite a lot in common, in the sense that they show layering, they show inhomogeneous mixing that resembles phase separations in statistical physics. And this has become quite clear when some of us, we were running in 2021 a similar program with the KITP, comparing plasmas, oceans, atmospheres, etc. And it became really apparent that those systems had a lot in common. So why would we care? And why I think this is a very timely and interesting thing is because the mathematical foundations of what the overarching principles are unclear. And it's very nice to have in the same place people doing a lot of those different systems to see whether or not we can find some common ground and some common principles. And transport properties also of layered systems are very different. So that's a very important thing to understand.
So I'm Anna Frishman from the Technion in Israel. And I think there are several challenges in this field. So one challenge is that the dynamics is strongly nonlinear. Another challenge is that, well, because it's strongly nonlinear, it's very chaotic, and that means that you need a statistical treatment. And that statistical treatment is out of equilibrium. So kind of the combination of all these properties means that there isn't a well-defined framework or well-developed framework to how to treat these systems. But I think what is another challenge, but at the same time an opportunity, is that there are many diverse systems where these sorts of phenomena happen and occur, and the opportunity is that when you could try and tease out the important ingredients and learn something from the different systems and what's common to them and what's different between them, and take out something that would give you the essential features of the phenomenon.
Right. So I'm Bruce Sutherland. I'm from the University of Alberta. So my background is in atmosphere-ocean dynamics, so I'm particularly focused on the application there. When we're looking at this idea of anti-diffusion, we're really looking at not just random systems becoming ordered, but also looking at transport barriers. And I have two examples in mind. One that many people will know about is the ozone hole. And so there you have a strong current in the atmosphere that circles Antarctica. And it separates the air in the stratosphere from the equator mid-latitudes that produces ozone from all the air that's right over Antarctica. And that's why the hole forms, because it's being depleted, but that barrier of this jet the air can't cross the jet and replenish it. And we don't have an ozone hole in the northern hemisphere, at least it's not so strong. And that's because we have mountains from the continents, and those launch waves which then disrupt the jet that's trying to form. And so we do get that mixing. So one thing we're trying to do here is understand what forms these barriers and also what processes disrupt it. And another application I have in mind is something that's not so familiar to people, is looking at what are called density staircases in the ocean. And this has been discovered just recently in the Arctic Ocean. Between the sort of pressure and colder water in the surface, you have hot and saltier water that originates from the Atlantic at depth. And that forms a staircase where the density jumps and is constant, jumps and is constant. And that's another barrier. It keeps that warm, salty water at depth from rising up to the surface. And that's a good thing, because if it does actually make it up to the surface, then it can act as a mechanism to enhance the melting of ice in the Arctic, which is already melting rapidly. So people are very interested now in how these staircases form, how stable are they, will they change as the climate changes, and hence produce a positive feedback that might lead to more melting in the Arctic Ocean.
Okay, so Patrick Diamond from UC San Diego. On the subject of other impacts, I mean, and you know, you've heard about impacts on climate, a kind of related question moving from the problem to a possible solution is on magnetic fusion, and particularly magnetic confinement devices such as tokamaks, which, for example, JET here in the United Kingdom is a prime example, and Europe is building, and the world are building ITER in France. And a major issue in magnetic fusion is confinement, and for that end, the program is very interested in barriers, and you've heard about the ozone hole, which is an example of a barrier. And I mean, barriers are extremely good for optimizing confinement, but they have certain negative aspects to them. And an interesting alternative is a kind of distributed barrier or a staircase, which is an example of layering, which is one of the things that is being studied in this Newton program. And one of the things that's under scrutiny is how to optimize and control and tailor the staircases for the best confinement result. And in terms of other impacts of the program, one interesting thing that has emerged is shall we say, an alternative view of the staircase in terms of the consequence of interaction of resonances rather than a rollover in the flux gradient curve. And this emerged from a kind of novel, unusual sort of interaction that occurred here between plasma physics and biophysics, which is the idea of an interdisciplinary mixture here has, I think, led to an interesting idea that can be exploited in this context.